Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 8 of 9. In Part 7, we learned that correlation is the cosine of an angle between two centered variables. A cosine never exceeds 1 in size, and that single geometric fact translated back is the famous Cauchy-Schwarz inequality. We prove it cleanly with a non-negative parabola, then redraw Maya's three scenarios as three angles between two arrows. Risk, we will see, adds like vectors, not like numbers. In vector geometry, the cosine being at most 1 in size is equivalent to the Cauchy-Schwarz inequality. The size of an inner product is at most the product of the lengths. Translate through the dictionary and you get, for free, that the size of the covariance is at most the product of the two standard deviations, hence the size of the correlation is at most 1. You can prove it without ever saying the word geometry, using the same one-variable knob trick that reappears in Gauss-Markov. For any real number t, the variance of x tilde minus t times y tilde cannot be negative. It is an expected square. Expand it, the variance of x minus 2 t times the covariance plus t squared times the variance of y. The right-hand side is a parabola in t that never dips below 0, so its discriminant must be at most 0. That rearranges to exactly the covariance squared being at most the product of the two variances. Equality holds only when some line, x minus ty, has 0 variance. That is, x is an exact linear function of y. The vectors are parallel, correlation plus or minus 1. So, the boundary of correlation is precisely perfect linearity. Back to Maya, now with a picture. Her two assets have volatilities 0.20 and 0.10, so by Cauchy-Schwarz, the covariance is boxed into a size of at most 0.02. That is why scenario A used a covariance of exactly 0.02. It is the most the assets can possibly move together, correlation plus 1, angle 0. Her three scenarios are three angles between two arrows of length 0.20 and 0.10. Scenario A, correlation plus 1, angle 0. The arrows point the same way, and the combined arrow is as long as it can be. Maximum risk. Scenario B, correlation 0. Angle 90 degrees, perpendicular arrows, and the combined length obeys the Pythagorean theorem shorter than adding the lengths, the free risk reduction. Scenario C, covariance minus 0.01, so correlation minus 1/2, angle 120 degrees, the arrows split apart past a right angle, partly cancel, and the combined arrow is shorter still. Portfolio volatility is literally the length of the vector sum, and the law of cosines for that sum is identical, symbol for symbol, to the weighted variance formula. Risk adds like vectors, not like numbers. To summarize Part 8, the fact that correlation never exceeds 1 in size is exactly the Cauchy-Schwarz inequality, and we proved it from a single non-negative parabola. The variance of x minus ty, which can never go below 0, forces its discriminant to be at most 0. Equality holds only at perfect linearity when one variable is an exact linear function of the other. Maya's three scenarios become three angles between two arrows. Aligned arrows give maximum risk, perpendicular arrows give Pythagorean free reduction, and splayed arrows partly cancel. Portfolio volatility is the length of the vector sum, so risk adds like vectors. Diversification is just the triangle inequality doing its job. In Part 9, our finale, we stack every pairwise covariance into one matrix, the object we2's matrix regression feeds on.